So when light gets into a material, the light in general will slow down relative to the vacuum. And so there's this quantity that's called index of refraction that's in words defined like this. So what you do is you take the speed of light in vacuum, and then you divide it by the speed of light in the material. Okay, so in terms of, that's in kind of plain English. In terms of symbols, the symbol we'll use for index of refraction is n equals the speed of light, as we mentioned up above, is c. And by the way, that happens all over physics, that you use the speed of light in vacuum as c. Very important constant. It's even the c that's in E equals mc squared, which we'll actually look at later this year in this class. C over v, like v for velocity, but the speed of light in a material. So just by way of like a couple examples, so this is going to be a property of different materials, okay? So let's list a few important materials that we'll look at. Well, one easy one to look at is index of refraction of vacuum. Right, now if you stop and think about what that would be, well, if the material we're talking about is vacuum, well, the way it's defined is you take the speed of light in vacuum and then divide it by the speed of whatever material you're talking about. So if you're talking about vacuum, that index is 1.00, you know, and so on. It's 1 exactly. Okay. Just a couple examples, important examples. We'll talk about water. We'll have light going through water a lot in examples that we look at. Water, it's about 1.33. Okay. A couple other interesting materials or ones that we'll use a lot. Index of refraction of glass is 1.52. I know there's different types of glass, but I think they call it crown glass, standard glass, 1.52. Notice what this means. The bigger this number gets, right, that means the speed of light in the material is getting smaller. So so you'll see this number growing as we get to materials where it goes slower and slower. One more that's really interesting is diamond, right, which is 2.42. So you can see the light really slows down in the diamond. And then final one up here, just a list. We will also talk about light going through air. For our purposes, it's going to be close enough to 1 that we're going to treat it as 1. Okay, it is slightly slower in air than in the vacuum, so really it's going to be like a little bit above this. But for our purposes, it's close enough, and so the index of refraction in air is going to be 1. Now, something to notice is, think about this for a second. What would it mean if the index of refraction were less than 1? Well, if you look how it's defined, then that would say the speed of light in vacuum is less than what it is in the material, and you can't get light to go any faster than in the vacuum. So n, and maybe it's worth jotting it down, n is always, it's less than or equal to 1. So if you ever get an index of refraction, it's greater than, my goodness. Okay, that's written very messy. I'm going to write it neatly up above. It is greater than, I misspoke. It is greater than or equal to 1. Right, you can't go below 1, because then that would say that the speed in the material is actually faster than the speed of light in vacuum, which we'll never see. All right. So that's this quantity called index of refraction. Again, just a property of a material, so often you'll just look it up in a table if you don't have it already. And no, you don't need to memorize it. You'll sort of come to know it though, because we'll use those materials so much. They're just easy, clear materials to use, and they're all around us, so glass and water and air. We'll have light going through those things. Well, so if you take a little bit of a closer look at what's going on when you have light going into a material. So imagine this being a beam of light coming down from the air, okay, where the index in air, if you remember, is 1.00, close enough to 1.00 anyway. And it's going to go through through glass, which has a higher index. So we'll say 1.52, and then back to air, 1.00. Right, so here comes the light. Now what we want to think about is, here's the direction that the light ray is going, and then what these are the wave peaks. So imagine these things being the wave, the peaks of the wave as the wave impinges on the surface. Okay, so what you want to think about with this, and it's a silly little analogy, but it really gives you insight on what happens when the light goes into a material, is think about these peaks being kind of like rows of people in a marching band, okay, and they're propagating along like this. And what you can think about is when you're out here in the air, which is low index, the light can go really fast, okay? So it goes really fast, and then when the light ray gets to the material where it's slow, so say this row in the front, so everybody's marching along, and then suddenly just this front row starts going slower, well, meanwhile the back row still gets to go fast until it gets into the material. So what you'll see is the wave front, or the marching band row that's behind, will start to kind of catch up. And so ultimately what that will do is put these guys closer together when they're inside this material. So it'll kind of bunch up like this. Right, because it's slowed down. So you can imagine it like the marching band was on the asphalt, and then they got to the grass, long grass, and so then that made them slow down. And then you can see what's going to happen on the way out of this material. It's like these people in the front will be back to the asphalt, so they can kind of tear off out of there back to high speed. And so then what happens is those wave fronts will space right back out to where they were on the way in. So it just gives you a little bit of a picture of what happens here. Okay, so this distance between the wave peaks out here we could call wavelength 1. Okay, and then this distance between the wave peaks here we can call lambda 2, and you can see that the wavelength of the light is going to be smaller in the slower material. Okay, so something kind of useful we can do with this is, if you go back to how the definition above, how index of refraction was defined. So we had n is c over v. Okay, well, the speed of light c, if you just solve for it, that is a constant. It never changes. Well, so since c equals nv, that means the product of n and v needs to be a constant. So what you can do is you can say, well, n1 v1 equals n2 v2, right? Because the product of n and v in this material needs to be the same as the product of n and v in that material. Okay, so we're going to derive a couple useful things here along the way, but what this lets you know, well, and we kind of already knew this, this basically implies that a larger n means a slower v, but that was kind of true from how we defined it. So larger n, smaller v. The bigger the index is, the lower the speed. Okay? But it turns out this is actually pretty useful, because what you can do, if you remember, well, how do we find out the wave velocity? If you remember voting for Elf Landon, you can multiply the frequency and the wavelength. So if this is true, then it also has to be true that n1 f1 lambda 1, because f lambda is v, equals n2 f2 lambda 2. Okay? Now let's think about this frequency for a minute. Say you were standing out here and kind of counting the wave peaks as they come by. So the waves zooming by, and every so often the wave peak comes, pop, 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 they come by. When you're in the material, the wave peaks are closer together. So that effect of being closer together might make somebody tend to think that you will see them more often, right? But what's happening to counteract that is they're going slower. So the upshot is that, yeah, these wave fronts are far apart, but they're going really fast. These are closer together but going slow. So the upshot is you see them come by just as often. Like if you were counting how often the peaks come by, pop, 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 they're arriving at the same with the same frequency. So as it turns out, the frequency of light never changes when you go from one material to the other. Okay, so we'll say, but F1 equals F2. And then the thing I want you to remember is when you go from one material to another, the frequency doesn't change. Does not change. By the way, that's worth a little skull and crossbones, because they will try to ask things like that sometimes on the AP. And they'll say like, oh, if somebody doubles the index of refraction of the material, what happens to the frequency? And then you can say, well, nice try, nothing. Okay, nothing changes. Associate color with frequency. The light doesn't change color just because it's inside of glass or inside of water. Okay, so the frequency is not going to change. Well, if you notice, if F1 and F2 are equal, right, these two things would cancel out on the two sides, and so then you get this super useful thing that N1 lambda 1 is N2 lambda 2. So that's kind of worthy of these are all kind of worthy of a little box and some stars, okay? So what this thing is telling you is basically if for a larger N, a larger index, which means where the light is going slower, you'll get a shorter wavelength. Okay, so these are pretty useful relationships that you can figure out from basically from V equals F lambda, and knowing that the speed of light in vacuum is a constant. Okay, so you can have this picture of the marching band comes in, they get into the material where it goes slower, and that bunches these guys up. And then when you leave the material, when you go from the grass back to the asphalt, then these things go kind of tearing away, right? So that's if you shoot the light kind of straight down, right? What we're going to do now, and this is where it gets really interesting, is we're going to look at when you shoot the light in at an angle. And if you continue to use this little marching band model, you'll see that it helps explain some of the interesting behavior that we see with light. So now what's happening is we're shooting light at a few different materials. You basically have like a puddle of water on top of a slab of glass, and then it's like air underneath. So if you remember, air has an index of 1.00, water is 1.33, so it's like a little bit slower in water than air. And then in glass, it's slower still, 1.52, and then down here we're back to air, 1.00. So here we go, we're going to shoot light in at an angle. Now, you have to imagine this would be like going from the pavement to grass to like mud, and then back to the pavement. Okay, so if you imagine the marching band, so here comes the marching band, and what's going to happen is as this row's marching gets in, this person here in the row is going to hit the slow material first. So this person starts going slow while this person's still going fast on the outside. Another way people sometimes see this is if you imagine like an axle with wheels, it's rolling in, and then this wheel's going to get hung up while this one can still roll fast, so you'll get a little turn here. Now don't get overzealous with how much you turn it, but turn it like a little bit, and these wave fronts will then get closer together with that same effect that we saw a moment ago. Okay, so again, it's this marching band model where you have the wave front coming in, and then this part of the wave gets hung up first because this is a slower material, and then it turns. Then, coming from this material, water, into a material where it goes even slower. So this part is going to slow down more while these people are maybe still up in the water, and so it's going to turn just a little bit more. Now it won't go to perfectly vertical, but it will go more vertical than it was. So you'll get something like this, and then these guys got to get even closer together. I might have gotten overzealous with how many I drew here, but let's just draw a bunch. We have to draw a lot more. And then when this exits, now the situation's a little bit reversed. Here comes the marching band, the row of people. This person is now going to get to the fast material first. So they take off while this person's still stuck in the mud, okay? And so they're going to lag. And so what's going to happen then is on the way out of this part peels out, this tears off while this is still hung up. And so you get this bending back the other way. And as it turns out, and we'll develop this more later, it will come out at the same angle. So you got to kind of imagine, I'm going to add a little dotted line here. That's a little dotted line. You're going to come out parallel to that dotted line. And you'll return to the original wavelength that you had when you were back in the air. Right, so it just basically gets shifted over. That light ray gets shifted because of going through the slab of material, right? A sort of cool thing about that is if you were, say up here, and I know this might seem ridiculous, but say up here is like a, here's a bird, okay? Here's a bird. It's not just a bird, it's an actual bird. Actual bird. Right, so there's a bird. Light rays from the bird would come down, get bent again, and then bend this way. So what would happen is if you were down here looking, so here's your pretty eyelashes, here's your eyeball, so here's your observer, so we'll say this is an eyeball. Okay, this person down here would come to believe that the bird, instead of being in that position, is actually kind of along this line. So what would happen is you'd have kind of like an image of the bird down here. Okay, so you kind of get faked out by this. It gets, since the light ray gets bent, so here would be like an image of the bird. Image of bird. Right, so you get faked out. So, you know, the bird hunter, I guess for some weird reason shooting through glass and water, I don't know. But if this person aimed where he or she thinks the bird is, they would shoot straight, and assuming the bullet didn't get deviated from the glass and water, the bullet would go through here and it would miss the bird. They would undershoot the bird. Right. You can see the same effect actually in water. So another example, I'm just going to put it off to the side. Here's like here, I'll put a boat on top so that we can see that this is water. So here's some water. Here is a bird above the water. Light rays from the bird would come down. Right? Water is a slower material than, here, let me draw the wave fronts. Water is a slower material than air, so that light ray would get bent like this. And so what happens is if you're swimming under the water, maybe we better give this person some fins, okay? Maybe a scuba tank, I don't know. So here would come the light ray from the bird. This person would perceive the bird being up here. Okay, so having the light ray hit this interface of materials can change the direction the light ray travels, and it can kind of distort what you see on the outside. And we'll see a few pictures of this coming up. So this marching band model, very, very useful. Think of the light ray coming in. This marcher gets slowed down while these are still fast, so it bends, hits the next surface. This one gets slowed down again while these people are still going faster. It bends again. Now on the way out, this marcher starts going fast, and so it kicks over this way, right? And you can play the same game with the water. Another key thing about this, just foreshadowing a bit, is any light ray path that we draw, it would actually be reversible if you shot the light the other way. So notice if we shot the light, if the light were going this way instead, the light ray would come in, get hung up quite a bit in the slow material, then kick this way as it gets into a faster material, and then faster still. And likewise with the light ray going out of the water. It would be in water, this part of the light beam would go faster, and it would bend like this. So these light paths are reversible. That can be very useful later on.